Chapter 11, Liquid Solids and Intermolecular Forces. Okay, we're going to start off with a video here. This is a photograph of an astronaut on the space station, and that is water. Okay, one really large drop of water. Fine. It's not supposed to be so hard.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and had you used equipment that was here on board the space station, we might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed in. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck,
Save space and space.
and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
Floating microphone distracts me. Will not stay put.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
Isn't that weird?
It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Oh yeah, we should have
The
watched this
automatic
the other day.
pipette is used to accurately transfer small volumes of liquid.
I always mean to show you that video about how to use the auto pipettes, and I always forget. Okay. So, any questions about that video? Any comments? Having issues with the lights.
Yeah, that's fine.
I don't really want to promote sleeping. It's not right now. So the water behaved differently than it does on Earth, right? Because of the lack of gravity. But it demonstrates one of the things we're going to talk about in this chapter, which is intermolecular forces. These are the forces that exist between molecules, hence the name intermolecular forces. Intramolecular are within molecules, and those would be bonds. These forces are significant only at short distances. They're responsible for the very existence of liquids and solids. Without them, everything would be a gas. And they are essential for physiological processes. They have a lot to do with enzymes reacting with the correct substrate, with your DNA staying together and replicating and all sorts of things. So whether a piece of matter is a liquid, a solid, or a gas at a given temperature depends on the relative strength of the intermolecular forces compared to the thermal energy at that temperature. So looking at the three different states of matter, we're familiar with water in all three of these states. We call water in the gas state a steam, and then we've got liquid water and solid, we call it ice. The densities of liquid water and ice are similar. The density of steam is much lower. Here we have illustrations. Solids and liquids are touchingly close, the molecules, and in a gas, there's big distances between them. So the intermolecular forces, depending on the distance, in a gas, there's really no effect of the intermolecular force, whereas in a solid and a liquid, the intermolecular forces are much more important because the particles are closer together. So liquids and solids are similar in some ways in their density, for one thing. But what's different about them? Well, if you pour water into a bowl from a cup, the shape changes, right? If you pour an ice cube from a cup into a bowl, it just stays the same shape, right? And that's one of the significant differences between liquids and solids. It's freedom of movement. So in a liquid, the particles are close to each other, but they can move relative to each other, whereas in a solid, the particles are fixed in fixed positions relative to each other. They are still moving, but they're not moving relative to each other. And so I mentioned before different states of students. Right now we are in the solid state, and you're sitting around the benches and you're moving, but not relative to each other. In lab, when we mill about, then we are like a liquid. So in a solid, it has a definite shape and a definite volume. And this is because the intermolecular forces are strong relative to the thermal energy. Thermal energy is going to vary with temperature. If we have moderate intermolecular forces, now those forces are strong enough to hold the particles touchingly close, but not strong enough to keep them from sliding around. And so the shape can move. Weak intermolecular forces allow the particles to separate from one another, and now the volume can change and the shape can change, and the density is much lower. Any questions yet? This seemed like a nice, easy topic after molecular orbital theory. It's like, ooh, finally. So here we have an illustration of a liquid, liquid water. Liquids take on the shape of their containers. Gases also take on the shape of their containers, but gases can be compressed. If you have a liquid in a piston assembly like this and you put pressure on it, you can't squeeze them any closer together because there's really no empty space there. And so you cannot push them together. Whereas with a gas, there's lots of empty space. If you put pressure on it, you can squeeze the particles closer together. Because what's between the particles is not air, it's nothing. The particles are the air, right? And you can squeeze them closer together. Sometimes people say, well, there are solids that are compressible. What about a sponge? Yeah, A sponge has a very open structure with a lot of air in it, and when you compress that, you're just squeezing the air out. We're talking about real solids. There are different kinds of solids. We can have crystalline solids or amorphous solids, and these have to do with how the particles are arranged. Amorphous means without shape. So there's no long-range order. It's just sort of random, jumbled together, like this picture here. Just a bunch of marbles stuck together. A crystalline solid has a regular order that repeats in 3 dimensions. When we change states, those changes in state usually happen at specific temperatures, right? We all know that if you want ice to become water, you heat it up, right? So when we take a solid and make it into a liquid, we do that by adding heat. We're increasing the thermal energy of those particles. And so with students, that would be like you're getting more energy and you're getting antsy, right? And you're just like, I don't think I can sit, and you're tapping your foot and you're just like, right? There comes a point where you just have to get up and move. That's when these get enough motion, thermal energy, kinetic motion, then they can partially break free from those intermolecular forces that are holding them in place. And then they can move around. So we've partially broken the intermolecular forces. If we continue to heat that up, these are going to move faster, and they'll become able to completely break free from the intermolecular forces and enter the gas state. To reverse the process, we're going to, for a gas, we'll either cool it down or increase the pressure. Increasing the pressure is going to cause these guys to get closer together. Cooling it down is going to cause them to move more slowly, and then when they bump into each other, they're going to interact, and they may stick together, and that's when it condenses into a liquid. Going from a liquid into a solid, again, cooling it down, reducing the amount of thermal energy, now we have relatively stronger intermolecular forces, and the particles get locked in place. Does that make sense? So here's an illustration of a propane tank like you might use for your backyard barbecue. It's called LP gas, LP for liquefied petroleum. It's mostly propane. It's a liquid, right? But when we open the valve, we don't have liquid coming out. We have a gas coming out. It's a liquid here at room temperature because of great pressure. And why would we want to do that? Well, liquids take up a lot less volume than gases do. If you're trying to cart this around as a gas, you're going to need a giant tank, right? Whereas you compress it into a liquid and you can have a smaller tank. When you open the valve, you're releasing pressure and allowing some of this to vaporize, and then it's going to escape because of the pressure difference. As the particles that are in the gas state here escape, they will be replaced by more particles escaping from the liquid.